All right. Yeah. Thank you very much. Before we start, I would want to say it's a great pleasure for me to be opening this year's Pappalardo Symposium, and I want to join Richard in saying a big thank you to Neil and also to Jane for their generous support to the department and for this fellowship program in particular, which is enabling all this great research that we're going to hear about today. All right, so I'm going to tell you a little bit about the first results from the new James Webb Space Telescope, which is currently really revolutionizing our understanding about the early universe and the formation of the first galaxies and quasars and black holes on almost a daily timescale. All right, so JWST launched on Christmas Day just a little bit more than a year ago. It launched from French Guiana in South America and was on its way to L2. L2 is one of those equilibrium points in space where the forces cancel out. And so it's fairly easy, or at least fuel efficient, to keep the satellite on a stable orbit. L2 in particular is about 1 million miles away from Earth, which is about 4 times further away than the Moon. The first public images were released in the summer of last year. You might have all seen the press conference with Joe Biden. And since then, the images of JWST were like absolutely everywhere. You could almost not escape them. They have been covering the front pages of all major newspapers. The gigantic banners of them were displayed on the Times Square in New York, for instance. The band Coldplay is showing the images in gigantic stadiums during their concerts. And to my own surprise, JWST has even been covering the top of my wedding cake last year. All right, so now here's some of the first science data that JWST has ever taken, only a few weeks after science operation had started in August last year. And we have received some of these very early JWST data because we're part of a team working with JWST for many years now, or some of us for many years now. This is the team. You can see there's a very strong representation at MIT with 2 current and 1 former Pappalardo fellow. And the project is called Eiger, which is a famous mountain in Switzerland. And in this case, though, it stands for emission line galaxies and intergalactic gas in the epoch of ionization. All right, so this is some of the first data that we got from this new instrument. So what are you looking at here? It's a part of the sky, actually a fairly small part of the sky. It's only a fraction of the size of the Moon. And you see hundreds and thousands of galaxies. And I'm just going to highlight some of my favorites here. You see these beautiful clusters of galaxies. You see like loads of interacting galaxies with like tidal tails and so on. You see some very red, very dust-obscured galaxies. And you just see really weird things like these glowworm thingy galaxies here. But this is obviously not why we got the data. You can look at this. You can spend hours looking at all the detailed galaxies. But really, why we looked at this part of the sky is because of this guy here. This is a fairly boring-looking galaxy. But it's the most luminous high-redshift quasar that we know in the universe. So quasars are these galaxies that host accreting, growing supermassive black holes in their center, and this accretion process that makes the black holes grow makes these quasars so incredibly luminous. And this particular object here has a black hole in its center that's more than 10 billion times the mass of our sun, which is one of the biggest black holes that we know in the universe. And therefore, this quasar is one of the most luminous objects that we know in our universe. This quasar sits at the very edge of our universe. It's in the very distant past. Its light had to travel more than 13 billion years before it hit the mirrors of JWST. All right, so the image itself, you can see, is composed out of 3 individual images. You can see the names of those filters in the top corner. They're basically just telling you the wavelength of these images. So it's about 1, 2, and 3.5 microns. That means that's infrared light, a bit longer wavelength than the visible. And JWST is really optimized to observe these these slightly longer wavelengths, this infrared light. And that makes it so incredibly powerful to observe the early universe because, as we all know, the further back in time we look, the more stretched, the more redshifted the light becomes. And so that's why JWST is really so well suited to look at this very distant past of our universe. All right, so we're not only looking or getting images of this part of the sky, but we also put a grism in the light. So we get a spectrum of every object on the sky. And this is what you can see here. This is some of our actual raw data that we're getting. You have the wavelength on the x-axis and then the position on the y-axis. And so you can see that the quasar, for instance, which is this bright star-like object on the lower left, you can see how it projects, gives this really strong spectrum at the same, in the wavelength axis, and you can see all the other galaxies, how they project, and we get this spectra of these galaxies. But you can also kind of see that it might be very tricky to analyze the data because the galaxies like overlap, and so the spectra overlap, and so we have to figure out which spectrum belongs to which galaxy. But what we're really interested in, what we're really looking for, are these tiny little features there. Those are emission lines that arise from the gas within each galaxy. And in this case, we're looking for emission lines from a doubly ionized oxygen gas. And they emit light at a very specific frequency. And these specific frequencies, if we find those emission lines at these specific frequencies, it will allow us to determine the redshift and therefore the distance to every galaxy, basically, that we can see in this field. And so these observations have revealed an absolutely incredible number of 117 galaxies at around the redshift of the quasar, which is there in the middle again. So everything that is circled in blue are galaxies that are sitting just a tiny little bit in front of the quasar. Everything that is circled in white are galaxies that are exactly at the same distance from us to the quasar, and everything that is circled in red are galaxies that are even further away than the quasar and sit in the background of the quasar. And so this incredible wealth of galaxies in this quasar field enables now a whole range of measurements that we never even thought were possible before JWST. But before I go in a little bit more detail on what measurements we can do, I just want to take a step back and explain why it's so incredibly valuable to find these galaxies not anywhere in the universe, but around a quasar. And therefore, let's talk a little bit about a quasar and how their spectra look like. So quasars, as I just mentioned, are these extremely bright galaxies that host a growing supermassive black hole in their center. And they emit radiation over the whole wavelength range, from radio all the way down to X-rays. And so if we look at the rest frame optical and UV wavelength regime, the quasar spectrum consists out of a fairly flat continuum emission that's coming from the accretion disk around the black hole. And on top of that, there are these broad emission lines coming from the so-called broadline region, which are gas clouds that are orbiting the black hole at very high velocities. And so you can imagine this quasar basically as a little beacon in the universe that is illuminating the universe, the cosmic web of our universe, and giving us, like, at least along our line of sight, an idea about what the universe looks like. Now, this is not how we actually observe the light from the quasar. The light first has to travel through the universe until it reaches our telescope. And while the light travels, two things happen. First, the light becomes redshifted due to the expansion of the universe. And second, whenever the light from the quasar passes through a region of the universe that still contains some neutral gas in it, some intergalactic neutral gas, part of the light becomes absorbed. And so it creates this dense pattern of absorption lines, which we call the Lyman series forest, in the spectrum of this quasar. And so whenever the light passed through a region of intergalactic gas where the gas was ionized, the ionized gas can let the quasar light pass, and so you would see a lot of quasar light passing through if the gas was ionized, whereas if the gas was neutral, you would see the neutral gas would scatter the light away, and so you would see this absorption trough. And so basically what the quasar is giving you is a one-dimensional map along our line of sight of where the gas in the universe was neutral and where it was ionized. Now, why do we care about this? You've probably all seen this at some point before. it just shows a brief history of our universe. And what it shows is that at the very beginning of our universe, after the epoch of recombination, all the gas in the universe was completely neutral, right? During recombination, protons and electrons could combine to form neutral hydrogen, which made the universe transparent. The cosmic microwave background was released, and the complete gas that we had in the universe was in a neutral state. At some point, the first stars, the first galaxies, the first quasars started to form. They emit ionizing radiation, and they start to ionize the intergalactic gas. And so the intergalactic gas, or the whole universe, the whole gas in the universe undergoes a phase transition from being completely neutral into the ionized state that we observe it in today during an epoch that is known as reionization. And understanding the timing and morphology of the reionization epoch is one of the major challenges for observational cosmology today. And our quasar is sitting somewhere in this reionization epoch, this phase transition of our universe, and now provides a one-dimensional information along our line of sight of where the gas in the universe was neutral and where it's ionized. You'll actually hear a little bit more about reionization in Rohan's talk at the end of the symposium. All right, so if we look back at this image that I showed you earlier, so this is as we would see the image on the sky. You have the quasar in the middle and all the galaxies surround it. If we now look at this from a slightly different perspective and turn this around, what you see now here is basically the x-axis now shows you the distance to the quasar or from the quasar, so redshift basically on the x-axis. You still have all your galaxies that were circled in blue previously in the foreground of the quasar. The quasar is shown as the yellow blob there, and all the galaxies that were circled in red before are in the background of the quasar. But what you can see now is the spectrum of this object as well. And so we can now try to study the relationship between the features that we observe in the quasar spectrum, which tell us where the intergalactic gas is neutral, where it's ionized, and then all the galaxies along our line of sight. All right, and so I'm going to tell you two measurements in particular. This data set enables a whole range of exciting measurements now, but I'm going to focus on two in particular, and then I'm going to show you how we can use those galaxies in the foreground of the quasar as to understand which sources are ionizing our universe, which sources are the protagonists of our reionization epoch. And then in the second step, I'm going to show you how we can use those galaxies in the background of the quasar to understand some more about the growth and the age of supermassive black holes. Okay, so just to reiterate briefly, the idea is to use the quasar as a beacon through the cosmic web, through the intergalactic gas, to understand where the universe is ionized and where it's neutral. And so if we zoom into this region here, this is now a plot from a paper that was just published actually last week from one of my collaborators. And what it's showing you here now is the spectrum of this quasar. Now, opposite to the spectrum that you saw before, you see that almost no light from the quasar can actually pass through. Almost everything is absorbed because this quasar lies in the very distant past of our universe. And so a lot of the intergalactic gas is still very neutral. But there are these islands of ionized gas that you can see, where you can see flux light from the quasar passing through. And you can see that it's somewhat correlated with the red points, which are the galaxies that we observe now with JWST along our line of sight. And so one of the first things we could learn from this data set is that galaxies are the main driver of reionization. It was for a long time, it was an open question whether the main ionizing radiation comes from galaxies or the much brighter but much rarer quasars. And one of the main results that comes out of this is that galaxies are actually the main drivers of reionization. Now, we can actually now go a step further and try to understand what type of galaxies are causing the reionization epoch to proceed. And how is it whether it's the smaller galaxies or brighter galaxies, larger and brighter galaxies, and how this depends on the environment in which the galaxies reside. Because if you go, for instance, closer to the quasar, you can see the quasar has already ionized its surroundings, You can see this by looking at the spectrum. There's a lot more light from the quasar being transmitted, indicating that there is a lot of ionized gas there. And we can now try to understand how the environment affects like the ionizing properties of those galaxies. This is still work that is ongoing. All right, in the second part, I just want to like show you how we can use the galaxies in the background of those quasars to try to understand a bit more about the growth of the supermassive black hole that resides in the center of this object. All right, in order to do this, I'm just going to show you the same plot that I just showed you, but in a slightly different way. So you still have the quasar sitting there in the middle of the image. All the galaxies that are in the background are shown in red, and everything that's in the foreground of the quasar is shown in blue. Now, instead of using the quasar as a beacon through the intergalactic medium, through the universe, what we want to do instead is use all the little galaxies in the background of the quasar as little tiny mini beacons to understand what the environment of the quasar now looks like. Because the quasar ionizes its surrounding, it also emits ionizing radiation and creates this bubble of ionized gas around it. The reason it has this parabolic shape is simply due to the light travel time. So everything that's in this illuminated region can reach our telescope on Earth. And so the longer the quasar shines and emits ionizing radiation, the larger is this bubble, this ionized bubble of gas that the quasar creates. And while the quasar emits this ionizing radiation, the black hole in the center of the quasar is growing and accreting material. And so if we can figure out how much time the quasar has to ionize its surroundings, we can understand what are the time scales of the growth of the black hole in its center. So these are just some simulations that we run to show you how these spectra should look like. You can see the ionized region around the quasar, and then wherever the gas is ionized, there's a lot of light from these galaxies coming through, passing through the intergalactic medium, whereas when it's neutral, you don't see that flux coming through. And then you can play around with like different ages, of course, and like different geometries, outflow geometries, to try to understand which areas have been ionized by the quasar and which haven't. And so there's a lot of modeling going in here, but basically there's two different scenarios that I'm just showing you here. If we find a very small region of the universe being ionized, that means the quasar is very young and the black hole growth must happen very, very fast. Whereas if you see a much larger region being ionized, but maybe inhomogeneously, you can tell something about the obscuration of these quasars. Now, JWST is great for finding these very distant, very faint galaxies, but it's actually not that good for getting the spectra of those objects, because the wavelengths that we're looking at here are just at the interface between optical and infrared. However, this is a wavelength region we can observe from the ground, but our current facilities, these 10-meter class or 6 to 10-meter class telescopes that we currently have on Earth, are actually too small to get really the spectra of these very faint, very distant objects. But getting these observations from these very, very distant galaxies is one of the main science drivers of the next generation of ground-based instruments, those ELTs, those extremely large telescopes with like 40 meters in diameter. I have no idea what that is in feet. Mirrors. And the Europeans are already building one in Chile. This year is a drawing for how one of the American ELTs, the Giant Magellan Telescope, will look like in a few years. And so there's a great synergy between JWST in space and the ELTs on the ground. They have very complementary wavelengths that will really allow us to tell a coherent story about the early universe and the emergence of its first luminous sources in the future. All right, so I'm just going to summarize very briefly. I showed you some of the first data that JWST took about the distant, very early universe, more than 13 billion light years away from us. And I showed you how we can use the quasar as a beacon to trace the cosmic web and to try to understand what are really the sources of this reionization epoch, this major phase transition of our universe. And in the second step, I showed you how we can use the galaxies in the background of the quasar, which we didn't even know existed before JWST really, as little tiny beacons to map out the environment around the quasar and learn something about the growth of the supermassive black hole in its center. All right, so I'm going to stop here. Thank you very much, and I'm happy to take questions.
We have time for some questions. Neil?
Do you want a microphone or?
I can give you the microphone.
As loud as I can. I enjoyed your talk, and
Thank you.
again, it's about a field, this whole re-ionization era that presumably you're giving an indication of what was happening to cause the re-ionization era. The problem I've always had with this re-ionization era is the re. Because it's re-ionization, that somehow implies that it was ionized at presumably closer to the Big Bang first, then lost its ionization, and then goes through the process, as you pointed out, perhaps caused by the galaxies to re-ionization. Can you clarify that for me,
Yes.
please?
Yes, you're very right that this is just a very confusing name, really. So it's the first time the gas becomes ionized, really. What it might be, I'm not actually sure where the name comes from, but what it might be referring to is that pre-recombination, we had everything separately, right? We had protons and electrons and everything, and like a plasma not combined. And then during the recombination process, protons and electrons combined to form neutral hydrogen. And that's where the cosmic microwave background was released. But no, it's the first time the universe becomes ionized. No, it's a good question.
But it's a confusing point of saying
It's a very confusing.
re-ionization.
I apologize. It's not my fault.
That word's been used a long time. It's always trouble.
Yeah.
Yeah, Sarah, can you use the microphone, please? Just step up to the aisle there.
If there's a Pappalardo Symposium on one of those distant galaxies far away that have since evolved in those 13 whatever billion years, and they're looking across their universe with their Webb telescope, what would they be seeing as our galaxy was all that long ago, if anything?
That's a really good question. I'm not entirely sure. I think the Milky Way is a fairly common galaxy, right? So it's probably and it's a fairly small galaxy. So I'm not sure they would even see it. I think we don't see galaxies that are the size of the Milky Way. I'm gonna ask Rob because he did them.
But I think you would see the assembly, like the building blocks might start to appear, but you wouldn't see anything that
The
looks like
progenitor.
Would we be like that worm thingy, or would we be a bright quasar, or like what?
I don't think it would be, so I don't know, I think is the answer. So the Milky Way had an active phase. So the black hole in the Milky Way had previously some active phases. That's why we see large ionized gas around the Milky Way. I'm not sure how long ago that was, though, I have to admit.
Any other questions? Okay.
Galaxies in red and blue, they seem to cluster at a certain, I mean, everything is correlated, velocity, distance, and such.
Yeah.
And I was a little bit confused because that also correlated with the feature in the spectrum of the quasar.
Yeah.
So that seems to indicate, which I wasn't fully aware, that if we have the line of sight of the quasar and the quasar light is absorbed or not absorbed, that's a feature. But the universe shows this feature not just along the line of sight, but also to the left, to the right, to the top, and to the bottom.
That's right, yeah.
So can you explain on that? So I had assumed that, you know, every line of sight would be completely different, but I think your analysis showed that what happens in the line of sight in the quasar is also reflected what happens a small angle away from the line of sight.
Yeah, that's a really good question. Yeah, so every sideline is in principle different. That's called cosmic variance. So if we look at one quasar here and one quasar here, they're very, very different. If we look at small separations, the universe is indeed correlated. And so you would see very correlated structures. And I think what you're referring to is something like where you saw all these galaxies. So you can see, I think actually on this side, it says like the distance from the line of sight. And you can see it's fairly widespread out in the whole, like over the whole like field of view, basically, the galaxies that we see. And they all seem to be correlated because they all trace the cosmic web, basically. Does that answer your question? Yeah. Yeah, exactly. So all the structure that we have comes from the cosmic microwave background, and it's then just collapsing to the density fluctuations that we now see. And so the correlations are actually just getting more pronounced.
Any further questions? Sorry, you had some of these plots where you were showing like the bubbles of these reionized regions.
Yes.
And so I was just wondering if you could like explain a little more how I should read that plot, especially because like okay, so for the quasars, no, so you were showing something that like made me think of a light cone, sort of.
This one.
Yeah, and you had a similar plot for a black hole, and I guess I was most confused about the sort of the cone extending from the black hole. Yeah, I just don't understand how to read this, especially with the black hole, the cone extending back to further back redshifts.
Yeah, so this is just a simulation, and basically the idea of this is that you have your black hole or your quasar sitting where the yellow star is, and if the quasar emits isotropically in a bubble around it, you would have this. Let me go back to the one slide before. You would see something like this. So if the quasar is just started ionizing its surroundings, it starts to ionize its surroundings isotropically, you would see something like this, and this parabolic shape is simply due to light travel times because it has to arrive on our telescope. This is just a different scenario. So we model all kinds of different variations of this. But basically, you can imagine that the ionized region is much, much, much larger. But there is an idea that like quasars or any active galactic nuclei, which are any active black holes in the center, might not emit isotropically. There's like the galaxy around it, there's dust around it, and so you might have this biconical outflow that could cause some parts of the IGM to be obscured by your torus, by your dust in the galaxy. And then you would see something like that. You can imagine this much more complicated, much more inhomogeneous. But basically, everywhere where the quasar's radiation can ionize intergalactic gas, you would see this transmitted flux in the spectra.
And so actually the thing about this redshift is really like a redshift that not implicitly.
Yeah, this is just the distance, basically. Yeah. Sorry, yeah, the quasar is just a measurement for the distance in this case.
Okay, time for one more question.
Great talk, Christina. I really enjoyed it. I'm just curious how many, so this is one sightline. And I'm curious if the program will be getting more sightlines and how many. One thing we've learned from lower redshift quasars is the sightline to sightline variability in our inferences of the universe.
Right.
And if that you expect that to play a role here as well, and how much we're going to average down the uncertainty in the future.
Yeah, so we got one. So we have already 4 quasar fields. This is one. This is the first one that we got. We now have 4 of those. The whole program is going to look at 6. And so in the 4 that we look at, there's an extreme sideline to sideline variations. But the general conclusions that we can draw, namely that galaxies reorganize the universe, and some other conclusions about the environment of the quasar, for instance, they are true in all of them, but they're within the sidelines. There's a huge scatter in it. We will get, with various programs that have been so far approved, more than like 40 sidelines in the end. So I think that will give us a good idea. Obviously, we're asking for more data to analyze them. But yeah.
Okay, thanks. Let's thank Christina again.
Thank you.